My name is Dan Martin. I'm a staff scientist and group lead in the Computational Research Division at the Lawrence Berkeley National Laboratory. And my role in ECP is as the Level 3 Area Lead for Earth and Space Science Application Development. The ECP Earth and Space Science portfolio spans the range from deep inside the Earth to deep space. There are 5 sub-projects. I'll focus more on the EQSIM project before briefly describing the others. The goal of the EQSIM project is an end-to-end simulation capability from the initial rupture through the wave propagation in the regional geophysical domain to the details of soil and structure interaction with structures of interest. In this context, Exascale capability will enable better physics, allowing for resolving higher seismic wave frequencies, which are computationally expensive but will permit better understanding of the actual motions experienced at the scale of real structures of interest, bigger domains and finer resolution, allowing, for example, realistic soil and rock structure in a simulation of the San Francisco Bay Area, better coupling between soil and structures, and longer time simulations. As an example, this is a computational model of the San Francisco Bay Area, in a simulation of a rupture on the Hayward Fault. The epicenter is shown by the yellow star. And here are snapshots of seismic waves at 7 seconds after rupture initiation and after 14 seconds. Then the goal is to understand how structures respond. This shows the coupling of the regional geophysics at the top with a local soil structure model using a domain reduction method. And here are time snapshots of the response of the soil island building system. Many ECP applications have what's known as a figure of merit, often called the FOM. This is a rough measure of how much science is done in a particular run of the code. Over the course of the ECP project so far, EQSIM has seen an impressive 184x improvement in their FOM, most of that after moving to Summit. While part of this increase is from faster computers, that's not the whole story. They also leverage improved algorithms and changes to their code to adapt to new computer architectures, and they're helped substantially by teaming up with ECP software technology efforts like Raja and HDF5, wherever possible to leverage work being done elsewhere in ECP. Moving on to the other projects, carbon capture will likely play a role in the national energy and climate strategy. Wellbore integrity can be essential to some carbon capture approaches. The subsurface project is modeling crack propagation in a wellbore to understand failure. As an example, this image shows simulated pore-scale calcium concentration on a fracture surface. The E3SM MMF project is building on the existing DOE high-performance Earth system model by incorporating a new cloud-resolving approach known as superparameterization, which is uniquely suited for exascale capabilities. This has the potential to dramatically improve the quality of Earth system model projections. Models of stellar explosions are quintessential multi-physics simulations. The ExaStar project is coupling new physics capabilities together to produce supernova and neutron star merger simulations of unprecedented scale and fidelity. And finally, the Exascale project is creating new synthetic sky maps of unprecedented scale and physical fidelity. To give a sense of the scale of these simulations, the lower left image shows a 2D slice of the full domain for a simulation. The upper left is a zoom in of the circled region in the original plot. The upper right is a zoom in to the second image. And the lower right image is a zoom in of the third image. If you have any questions or comments, please do contact me. Thank you for visiting.